So, welcome to another CPD seminar. This is part 2 of my course on structural insulated panels. And today we'll be looking at how we calculate the structural capacity of these panels and how we calculate the axial and bending capacities of the panels. It's also another one of those, what does this spreadsheet actually do? Because Redcode does have a spreadsheet for this, and we'll present the answers using Mathcad. A reminder of the series, we've already had the first one on tiny homes 2 weeks ago, and that is now uploaded to the YouTube channel. This one is part 2, so we'll be looking at roofs and ceilings, walls, and beams. Yes, you can turn these panels into beams, should you so need to. In 2 weeks' time, we'll look at some case studies, look at cold stores and freezers. And on number 4, we'll be looking at the capacity of fixing. So that's more Mathcads, looking at the calculations for bolts, rivets, and screws in steel, as well as aluminium. And we'll be looking at the warm roof tables for load span tables created this year, and that will be the final for 2023. And that will be looking at transformed section properties using Mathcad, as well as the capacity of these composite panels using Mathcad matrices. So the sources and the references, well, there's a couple of old ones. The one on the left is an old report from New Zealand about the testing of these panels. The one on the right is more recent, and this is a German publication, because of course it is. There's also some useful information from the Conqueror website, and this gives you some technical drawings that you may find useful when you're designing these panels. On the right-hand side, we have basically a textbook that's available for download from the Profahol website, and Profahol is a Russian company selling these products into Europe. So the basics, look at our panels in bending. And no surprise, they look like a beam. We have 2 bits of metal, one at the top and one at the bottom. So in bending, one goes into compression, one goes into tension. And the role of the core, the insulating core, is to separate the two and keep them working together. And so in simple terms, we look at the plastic bending capacity and we take the yield and multiply by the thickness, multiply by the lever arm between the two. Strictly, you should take off a skin thickness for the lever arm, but as the skin thickness is normally about 0.5 millimeter, it really doesn't make any difference. Here is our usual strength reduction factor, and then we add something here called a K factor. Now the K factor is another fiddle factor, and it allows for wrinkling. So when these panels fail in bending, they really fail by wrinkling, and it's the buckling of one of the sheets, i.e. the sheet that's in compression. So this is what it looks like when it's failed in bending. You get a wrinkling of the top sheet, usually. Similarly for panels in use as columns, so under axial load, you can have the more conventional forms of deformation and buckling for columns under axial load, but you will also get the wrinkling again, whether it's on one side or both sides. So you've got to consider second order effects when you're looking at slender panels. And all you need to do is add another fiddle factor as an amplification factor, and apply that to the moments and to the deflections. So when a panel is subject to axial force, you can calculate the capacity based upon the area of the steel sheets and multiplied by the yield of the steel sheet, the yield strength of the steel sheet, and again use this K factor. But it's unusual for this to be the defining of capacity. You also need to look at the buckling loads due to the bending rigidity, and that's given by this formula here. And from that, you can derive the elastic critical buckling load. And that's usually this that dominates within a panel. Looking at shear, and it's the core that takes the shear. Here we're showing a polystyrene core, but they're similar failure in PIR. And so we look at the area of the core, the insulating core, and multiply it by the shear capacity of your core, and again use a strength reduction factor. Here is a little bit of crushing in the local area of bearing. So thinking about deflection, you'll probably be familiar with the first half of this equation. This is simply the flexural flexion under a uniform load, and we add the shear deformation, and then the shear deformation is in the core, the insulating core, in this case PIR. So we use the area of the core and we use the shear modulus of the core. We sometimes use these panels, particularly the roof panels, as bracing, and so we want to form a diaphragm. And so that means that loading on the ends of the buildings gets transferred to the side walls through diaphragm action within the panel. Now, if you've got compression at one side, you'll have compression in your joints. If you've got tension sucking at the other side, you'll get tension in your joints. And to form these as a continuous membrane, we need to connect the joints with rivets. And we also need a fixity all the way around to make sure that your panel actually works as a diaphragm. Similarly, in the other direction, so we're taking load across the building. We're using the roof as the diaphragm, and therefore the joints are now subject primarily to shear there. So your rivets are taking your shear from one panel to the next to enable it to act as a diaphragm and pass that load down into the walls. The simple way, and the simplest way of finding out the capacity of your panel, well, many of the companies provide load span tables, and this is one for thermopanel from Metalcraft. So if you're looking at, for example, a 150 thick panel, and your span is 5 meters, then the capacity is 1.2. And what does that mean? It's 1.2 kPa, and that's given as a permissible value. And they're usually looking at wind pressure for walls and roofs. That's normally the dominant load case, but not the only load case. And when we say permissible, think of that as the serviceability limit state. Some other manufacturers and some other panels provide graphs of load span tables. In this case, this is for uniform wind loads applied to the Aspire span panels. And similarly, we've got a range of thicknesses from 50 to 150. So if we're looking at 150 thick and our span is 5 meters, and here we go. We go back to our distributed design load in kPa at the ultimate limit state, and that gives us the number 3 in there. So there's quite a big difference between your ultimate limit state loading and your serviceability limit state loading. Now, Redco has a spreadsheet for this, because of course it does, and it's under walls, and you'll find the sheet called polystyrene panel design. Now, if you open that up, it'll give you some basic calculations for polystyrene panels. If you're using PIR panels, you need to change some of the parameters, and namely the density and the self-weight of the panel and the shear modulus that you're using. So we won't look at the spreadsheet itself. We'll look at the Mathcad calculations, which should mirror the spreadsheet. So let's open that. And this is a roof design. In this case, it's for a blast freezer. And we want to calculate the bending, shear, and deflection for a roof panel when it's subject to gravity and wind loads. So we've chosen a panel, and it's called a Techno panel, and that's from Metalcraft. And here we've got a span of 8.85 meters. That's quite a big span. And our panel thickness here is 200 millimeters. We look at the tributary width. So we're looking at the unit width of the roof. And conveniently, that's how wide the panels normally come, as 1 meter wide. Sometimes they come a bit wider. But it's much easier to relate to a meter width. Skin thickness of these, in common with many of the panels, is 0.59 millimeters. The panel mass you can take from your lookup table from your brochure, or you can work it out. We then derive the second moment of area for the skin and the second moment of area for the panel using the panel axis theorem as well. So from that, we can calculate the elastic modulus for the panel and the plastic modulus for the panel. And from that, we can later derive the elastic section capacity and the plastic section capacity. You will notice there's very little difference between the elastic and the plastic section capacity because it's all down to the steel plates in terms of bending capacity. The design shear capacity is down to the core. So again, we give the shear strength of the core and apply the strength reduction factor. Let's take our loading. In this case, we've got quite a number of services hanging off our panel. In this case, it includes sprinkler pipes. And so if you're ever designing these cool stores or warehouses, always ask whether they're sprinklered, because it makes a big difference to the load in there. So the loading of the services is much bigger than the loading of the self-weight of the panel itself. We allow a nominal live load, but at a nominal, in this case, a nominal wind load. So look at the different load cases and load combinations we've got. We've got the typical ones, the combined dead and live, just dead on its own, and then dead plus positive wind, and then your dead plus the uplift, wind uplift. And from that, you will derive the design moment. Take the worst case and compare it to your capacity. In this case, it's very efficiently designed and that your utilization ratio is 100%. You'll see that the shear is similarly compared with the capacity, and it's only a utilization of 27%. Okay. A quick check at serviceability limit state. So we pull out our short-term and long-term load combination factors, and we derive the deflection, as you've seen from the equation before, under the combined dead and live loads, short-term and long-term. You can also check the deflection under the service load. I've set the wind load deflection and the dead and live load deflection to be span over 200. That's entirely up to you. It's a bit of engineering judgment as to what the live load deflection and the wind load deflection should be limited to. Most of the published tables will limit it to span over 150. And if you're looking at a freezer, then there's going to be a big difference between the temperature inside your room than outside your room. And that will cause thermal bowing. And here's a little calculation as to the deflection induced by your thermal bowing. Okay, this then goes on to connection design, but that's for another day. We'll move on to the wall design. So same sort of panel. In this case, it's a mere 125 mil thick. It's a Matecno panel, and it's got a PIR core. So this is now a vertical panel, and it's subject to the roof loads, and it's subject to wind loads on its face. Same thickness of skin, and we've got the usual parameters of its capacity. We can derive the second moment of area for the panel and the radius of gyration needed. We can then derive the plastic section capacity and the elastic section capacity as before. We then calculate the buckling load and the elastic critical buckling load. I skipped over a nice little check on the panel slenderness. So we can do this panel slenderness check. Now our spreadsheet will tell you if it's more than 180, you've got an error. If it's more than 180, if your slenderness is more than 180, then you really need to think about the additional loads that are induced because of the slenderness. If it's below 180, they're probably not that significant. In this case, it's only a little bit above, so we have a little bit of an increase in the loading because of that. So once again, we take the loading. In this case, we've taken it from the roof and then we're applying it to the walls. We do our load combinations again, dead and alive, just dead on its own, positive wind downwards and wind uplift to get the worst case. We have an induced moment on all of these. Because you've got an axial load, you're saying that the load is applied at an eccentricity. This is a little bit conservative. We're saying it's applied at the face of the panel rather than directly in the middle of it. So from the geometric centroid of the panel, you then say it's a little bit off the distance from the next panel as well. So you're applying quite a big deviation, eccentricity, in this case 100 mil, which gives you an induced moment in each of these load cases. In many of the load cases, it's not that much, but it's not nothing. Then you want to check your wall panel for lateral loads. So the lateral loading or out of plane loading is usually the critical factor. And in this case, it's only taking wind, regardless of which direction it's in. And so you then take the worst case of the bending arising from the wind, and then you can compare that with your amplified moments from the axial load, and then compare the two. So compare your design moment with your plastic capacity. You'll see you've got a ratio of 60%. And you can look at the bearing, compare the applied axial load with the bearing area that you're assuming. So you're assuming the full width of the panel and the unit width length of the panel. And you'll see the capacity is fine. Again, shear is fine. We compare the applied shear, enhanced applied shear with this fiddle factor. Just pop back to see what the fiddle factor is. So this amplification factor is derived from the figures above based on your elastic critical load, and it only comes out as basically 1.038. So a small increase from your non-slender panel. And again, we apply the thermal bowing, and you'll see that's fine too. The next part of this sheet goes into connection design, which I'll reserve for next time. The final one is looking at using panels as beams. So here's the Mathcad for a panel beam design. So in some cases, you'll have openings and you won't really want to use a separate lintel. You can use the panel itself and turn it on its side and use it as a lintel. And the way you use it as a lintel is to employ the skins as your webs of your beam and apply a channel. So you rivet channel top and bottom. So we take our channel properties. In this case, it's a 150 by 45 by 1.55 steel channel. And we do the same for the bottom as well. We calculate the areas and the second moment of areas and the offset from the centroid. From that, we can derive, using the parallel axis theorem, the second moment of area about the neutral axis. If you don't like the units, you can always change them. That's the kind of joy of Mathcad. Have something slightly more sensible, it should change. If you don't like it in standard engineering form, you can change that into decimal form. And if you don't like all the decimals, you can reduce the number of decimal places to make it more of a sensible number. So we work on the elastic section modulus of the compound section and derive the moment capacity based on that, including our wrinkle factor. So for our beam, we've said our beam is 600 deep, and it's the panel width. And that gives you a 15.6 kilonewton meter bending capacity. The shear capacity is based on the webs. And again, we use our wrinkle factor in there to give you a 23 kilonewton capacity. So you compare that with the applied bending and the applied shear, and you find out your utilization ratios are just about good enough. If you don't like it expressed like that, you can again change that to a percentage and reduce the number of decimal places. So you have a nice round number. Okay, so that was the 3 sets of Mathcad, just looking at the capacity of the panel in bending and in axial load and creating a beam. So here are the references. There's lots of information on the Metalcraft website. There's also useful information on other product manufacturers, including Conqueror and Bondor. This Prof. Holodor is from Russia, so they've got quite a bit of information, including that technical manual. That's worth looking at if you're getting into the design of these panels. So that's the end of this seminar. Just a reminder, in 2 weeks' time, we'll be looking at case studies for cold stores and freezers. So no Mathcad, just lots of pictures and drawings. I've also noticed that a lot of viewers are watching but not subscribing. So 90% of my viewers are not subscribing to the channel. If you're seeing adverts, I'm not getting the money for them. YouTube is monetizing some of the videos, some of the lectures, but sadly I need another 900 subscribers before I actually get to see any money at all from this channel. So at the moment it's all done for the glory of Rome, as it were. So keep a lookout on this channel. Please subscribe and share the show with your friends, and hit that like button on the bottom of each video.